Hi everybody, can everybody hear me?
Yes.
All right, so today I'd like to talk about how we can connect humans and robots using embodied intelligence. Okay. So, what is embodied intelligence? So, embodied intelligence is a subclass of artificial intelligence that involves a system being physically situated in an environment. So, systems that display embodied intelligence are able to communicate externally, reason independently, and are able to interact and adapt to their physical environment. So, I think a great example of embodied intelligence is Wall-E from the movie. He's able to interact with the environment, reason about what his next step should be, and he's able to communicate with other robots. So embodied intelligence really sits at the intersection between robotics and artificial intelligence, and this intersection is booming with a lot of active research and development happening right now. So today, I want to answer a question from the field of embodied intelligence. How do we talk to robots and let them reason by themselves? And so this is a really, really fundamental question. And to understand how we can even start to answer this kind of question, we need to go back in time and understand the historical context of the field of embodied intelligence. So it starts here at MIT with Dr. Joseph Licklider. So Dr. Licklider was a psychologist and early computer scientist at MIT, and he worked on and pioneered many foundational concepts such as the internet, computer graphics, and time-sharing systems, well before they were the mainstream ideas that they are today. In addition to all of that, because that wasn't enough, Dr. Licklider was an early pioneer in artificial intelligence and human-computer interaction. So in 1960, while researching this area, he wrote a paper called Man-Computer Symbiosis. So in this paper, he outlined a vision for the future in which human minds and computing machines would be closely coupled together, working together in partnership. And so the general idea behind this paper was about how can we improve the interaction between humans and computers. So there's kind of a problem. The way that we talk and the way that robots communicate are two very different things. So we communicate through natural language, right? It's pretty much everyday speech. So natural language is flexible, it's ambiguous, and often requires some understanding of context to truly understand what a sentence means. However, robots communicate through machine code, and machine code is rigid, logical, but it's very limited in its expressiveness. So we don't talk in robot code at all. But the nice thing about robot code is that it can be executed independent of context. So it doesn't require a lot of pre-processing or something to that extent. So this is the problem that Dr. Licklider posed in his paper. The problem that we cannot communicate with robots directly. So there are a lot of solutions posed to Dr. Licklider's problem. So one of the earliest ones was mentioned before, symbolic AI. So symbolic AI is about using formal logic and structured reasoning to basically encode natural language into a way that that computers can understand through knowledge graphs and through relational tables. So the problem with this kind of approach is that it struggles with ambiguity. So it really requires a lot of rigidness even within natural language. And the arguably more important, the problem is that to make these kind of knowledge tables, it had to be done by hand. And this was an incredible amount of work, because think about how much effort it would take to encode the entire English language into some sort of knowledge representation. The amount of work would be immense. And this had to be manually created and updated over time. Eventually, deep learning methods took over symbolic AI in terms of natural language processing. So the most common types of this were recurrent neural networks and long short-term memory models. So these kind of work by handling data sequentially. So if you think about a sentence, it's basically a sequence of words. And the reason that these kind of model architectures are so good is because they're perfectly capable of handling sequential data, which allows them to understand context. So what words mean with respect to a sentence. And it can process long strings of data. It was also much more effective at understanding syntax and context as opposed to symbolic methods. But without a doubt, the biggest game changer has been large language models. And large language models are kind of separate from RNNs and LSTMs because it doesn't handle data sequentially in the way that we think about it. It basically handles language through context, but in one instance using transformers. So large language models have also shown to be really good at reasoning about things. They have very good lightweight reasoning powers. and they're also very good at understanding code. I think the human eval benchmark was mentioned before, and that is super important because it means that large language models can write code and write code very well. So it's obviously not 100% accurate. Hallucinations are still a real problem that face LLMs. But in terms of acting as a translator between humans and robots, LLMs are very promising in their ability to do that. So we can put a large language model between a human and a robot, and now we can say, look, we can start to talk to each other. So this brings us to the first part, which is simulation. This is the robot. I built this thing called a Robot AI Lab. So basically, it's an app that was, it's a proof of concept simulation that was to say, hey, can humans actually use large language models to provide natural language command to robots to allow them to move around and interact with their environment? So this simulation is it's a very straightforward one. It's a 100 by 100 grid. You can kind of see here. I don't know how well the colors are coming out, but this square in the center here, that's our robot. So it can only do it has a very limited feature set. It can move for speed, direction, and time. It can move to a specific point on this grid. It can pick up an item and put an item down. So these items here are these little circles, and they don't really do anything. They're more so of a proof that, hey, robots can actually interact with their environment. So they're a little 1 by 1 circle that robots can pick up and place down. So what happened is this entire simulation was written in Manim. So it's an animation library in Python. So I gave a prompt template to the Meta. So Meta is like Llama 70 billion parameter model. So I basically gave it a prompt template that told it, how the simulation worked, the rules of the simulation, what can you do and what can you not do, and how to effectively write code. So it basically, and then in addition to this prompt template, I passed it a user parameter, or some user input, like do this or do that. And this call would actually generate code based on the prompt template. And this code is then executed to render a video. So here's an example of a prompt. So this is the prompt. So place an item down in some random spot, pick it up, and move it to the top left corner. This is really hard for traditional computers to understand. I mean, there's a lot of natural language happening here. Some random spot, what could that even mean? And there's also obviously an order of operations that has to occur here. So once we gave this to the LLM, this is what it came up with. So you can see in the bottom here, or here, you can see this is the prompt, and now it's thinking about it. Eventually, it'll output some code. So you can see that here, it outputs some code. And what you can see is that it reasons through the steps, and it outputs its code. And now the robot moves to this random position, picks it up, and drops it in the top left corner. So you can see that the LLM was actually very successful at doing this kind of thing. It interpreted what random meant, it interpreted what top left meant, and this is something that we could never do before. And it serves as a really great proof of concept that we could actually talk to robots using only large language models. So the problem is that this is all still software, right? We're still in the computer. There's no real physical moving parts. So now it's the second part. We're gonna move to the real world. So this is a real robot. So it has 4 degrees of freedom. It has 3 arm joints and then 1 gripper joint here. So there are servo motors controlling each joint, and there's a camera mounted on the gripper. So this allows it to actually perceive the environment around it, and everything's powered by Raspberry Pi. So it's a very lightweight microcontroller, and this allows me to write code that could be sent to it. So what can this robot actually do? So same as before, it has a very limited feature set. So it can move to a point. So we can imagine that every point in front of the robot is created by some coordinate grid. And I can say I can move to a specific point in this coordinate grid using inverse kinematics, which allows me to give a target point, and then it can reverse engineer these joint angles. I can then open the gripper and close the gripper. That's just sending a servo motor signal here. And then we can detect color using OpenCV color contouring. So that's why this camera is mounted on here. So you can detect the color of the object in front of it. So it's a very limited feature set, but you can do a lot of things with it. So let's talk about how we can actually control this robot. So I can type in user input here, and there's a Vite server running locally on my computer. And this Vite server turns my user input into API requests. And these API requests are then sent to this fast API server running on the robot here. And this fast API server takes this API requests and converts them to actual robot commands that can be executed on the Raspberry Pi. In addition, there's an OpenCV server here. This OpenCV server is basically streaming camera data back to my laptop so we can actually see what the robot perceives. And it also allows the Fast API backend to do color processing. So we can actually control this robot here. So here's the camera of what the robot's doing, and we can see that. So this is the camera of what the robot sees. So I can say like grip close. So you can see that the gripper opens and closes. So you can say I can open the gripper and I can move to this point. And you can see I move down here, and then I can say, and you can see it picks up the item. So this is pretty much the traditional way of. This is pretty much a traditional way of how we would talk to robots, right? We can see that I'm writing code manually, and the robot would execute commands, but there has to be some kind of translation happening. There's no natural language involved. Well, how can we solve this problem? Same as before. We can throw a large language model in between the two, and now we can talk to the robot using only natural language commands. So now on the front end server, I can put a step in between. So I can type in my user input, but this time I can use only natural language. So I can speak to it basically. And now what happens when I can speak to it, I can now take my commands, send them to LLM. In this case, I'm using Claude 3.5, which is running on Anthropic servers. So I can send it to them. So Claude, I can send this information to Claude alongside a prompt template, similar to the one from before, which tells the LLM how to write code for this, which is then sent back to this Vite server, and this Vite server can now send its API request to the Fast API backend. So this is really how we can start to control robots and let them reason for themselves by using the power of LLMs to basically offload some of the work that humans might be doing in the past, and now giving it to an LLM, which can effectively be a translator between humans and robots. So we can go here, and if we click this button, let's move back. And now you can say, okay. So now we have basically, instead of a typical like terminal control interface, we can see that we can just type in natural language commands. So I can just talk to it as if I was talking to a person. So I can say like, hey there, pick up whatever is there. So I just asked it, hey there, pick up whatever's in the pickup area, and then hold on to it. So now it'll take a few seconds, but the LLM will come back with the request. Move there. And now I can pick it up without me having to write a single line of robot code. And this can be extended to a lot of things. So now I can just tell it like, drop the item and don't move. So I just wanted to just drop the feedback. Now we can actually do a lot more interesting things. We haven't actually seen the ability of it interacting with the environment. So now I can tell it, why don't we sort it based on its color? So I can just say, so it detects that the color is red, it grips onto it, and it's able to put it right where it belongs without me having to write a single line of code. This is an entirely automated pick and place activity, which is something that I don't think anybody could have dreamed of doing maybe 5-10 years ago. Fully automated without me having to write a single line of code. And we can actually now start to get a little more creative with it. Because now it basically functions as an LLM, and LLMs we've established are pretty creative when it comes to these kind of things. So I can tell it to do something silly like dance. And now it's pretty much relied on the LLM to come up with some kind of creative reasoning to say like, how can we make the LLM dance? And you can see that it's kind of doing a little bit of a dance routine.
Dance.
So it's kind of just like moving back and forth. It dances better than me. So I mean, and then we can kind of make it do some things. Oh, it's still got more. So wait until it stops. That is done. So now I can actually make it do kind of similar things. I can say like draw a rectangle. And if it was actually holding a pen, you could actually see that it would actually draw a rectangle. But you know, the interesting thing about LLMs is that you know, they weren't initially used for human to robot code. They were initially, the idea of transformers came out of language translation. So what we can use now is we can actually speak to a robot in different languages. It's not just English. So now the funny thing is that if I say that, let's say I put this red cube in this green spot here, right? I want to tell the robot that there's something incorrectly placed in this green spot, and I want it to pick it up and put it in the right spot. I can tell it to this in Spanish. So I just type this in. Wow. So I typed a fully Spanish command. There's not any English. And you can see. And without writing a single line of English language as well, I'm able to talk to a robot fluently without any issues. And it was able to correctly place the red cube in the red spot. And so you can kind of see the power that LLMs have in acting as a bridge almost between humans and robots. So yeah, that's it. Any questions?
So no,
Go ahead.
you obviously have a mat there.
Yeah.
If you flipped it around, would it do the same thing?
No, because I gave it the coordinates on the map. But I mean, this OpenCV algorithm is pretty simple. But I imagine that if you keep extending like OpenCV to actually do some like image processing, that it could actually work without any knowledge of the map whatsoever.
So are there guardrails or kind of, you know, specific rule sets that you gave it? For example, if I tell it self-destruct or whatever, what would happen then?
So there are some rule sets. Like I gave it the rules of basically the prompt is that it's a robot that generates safe JavaScript code, and I gave it 10 rules basically of how to manipulate. Like before you inspect anything or grip anything, you have to open the gripper, and then when you open the gripper, you have to wait 1 second to let the gripper open. So basically some kind of rules. But self-destruct, I actually don't know what it would do to that. So let's see.
Yes.
Self-destruct command not recognized or implemented. Robot continuing normal operations. So there is some level of basic safeguards that these large language models that are open to the public that they've implemented, right? I think that some kind of instruction like that would be like blocked or filtered out.
I think you were here last year, right?
Yeah.
And you were doing this similar demo, but it was all digital. You didn't have a physical
Yeah.
prototype, right? So congrats. And also, what did you do to take it from that prototype from the last year to this year? What was the work involved? And do you consider this an evolution of that?
Yeah, I definitely consider it an evolution of that. So last year, everything was written in Python. Python's a great language. The problem is it doesn't really get along with browsers that well. So the first step was to move everything over to JavaScript. And in that 1 year span, large language models have gotten so much better. So, and also gotten so much cheaper. Like Claude 3.5 is very inexpensive to run now. So that's why I was able to switch over to a much more powerful model for actually cheaper than what I was running before. And the hardest part of getting this thing to work was honestly getting this physical part assembled and running with the fast API backend. After I could send commands to it like through an API, the rest was pretty straightforward. It was just designing a front end to like send commands through it. But those are pretty much the steps involved. So first it was translating from Python to JavaScript, then constructing this backend here, and after that it was just about attaching a front end in front of it.